Hi everyone, my name is Teja, and today we're going to talk about classifier performance analytics actually, and it's about 20 minutes or so. The objective of this module is to communicate classifier performance as well as evaluate different classifiers, uh, and this evaluation is closely tied to your business goals. Okay, so to communicate how well your classifiers are performing to business stakeholders, as well as to understand how your classifiers are performing with metrics which are beyond just accuracy. So in that context, we're going to talk about three techniques, or three plots. One is the profit curves, the second is the cumulative response curves, and the third is the lift curves. And to get into the topic, we will need to know a few things. First is what is an expectation or an average. A little bit of idea of what a random variable is, as well as what is the likelihood of an event is useful. The second thing is we want to know what is, we should already know what is a classifier. We've already seen some classifiers before, potentially like decision trees or support vector machines and so on. We need to know what is the training data set and what is the test data set, what's the accuracy of a classifier, and what's a confusion matrix. Actually, I'm going to revisit what the confusion matrix is pretty soon. So what's the objective? See, the objective, as I mentioned before, is to communicate the performance of our prediction models, and we're going to focus on classifiers here, but it also holds equally well for regression models and so on to business stakeholders, and we want to do it in a visual way, and we're going to do that in a nice way where we're going to take the performance that we can calculate on test set, as well as some additional information like costs and benefits of doing something with the classifier, and then therefore we tie it nicely to the business goals. Okay. The types of questions that it can, this what we'll see today can answer is that we can say, is my model good enough for my application, or how can I measure if it is good enough or not? Okay. So let's recap what is some terminology. So a classifier. What is a classifier? It's a model or an algorithm which takes as an input an instance or an example or a feature vector and outputs a class or prediction. Okay. So for example, and we'll kind of keep it restrict ourselves to two classifiers here. So the output is going to be binary, which means it could be a buy or a not buy prediction in a marketing application, or it could be generally a positive versus negative assessment, a prediction. Now, accuracy of a classifier is just a single number that you output, which is the number of correctly classified instances out of all instances. For example, in your test set, accuracy is just out of all my test set instances, which instances did I predict correctly the class of that instance, each of the instances. Okay. Now, what is the confusion matrix? A confusion matrix and I'm going to talk about binary classifiers pretty much, is a 2 cross 2 matrix. So two rows by two columns, where the columns represent the actual classes and rows represent the predicted classes. Okay, so for each test instance, what you do is you know what its actual class is, and you also know what my classifier predicted for this test instance. Okay, and so if my actual is a positive and my predicted is also positive, I put it into the first cell. And similarly, if my actual is positive but my classifier predicted it as negative, I'm going to put it in the second row and first column. Okay. In fact, let me give you an example here. So let's say our classifier predicts, we are in a marketing application, and our classifier predicts whether this customer, if I do a targeted, ad or something, they're gonna actually buy or not. And so let's focus on the first column. So this column represents that there are 100 test instances, 100 people who actually bought, because of our ad. Okay, and uh, we also have the rows which present whether the classifier predicts that they'll buy or not. Okay, and so here you can see that here the classifier has 100% accuracy because it's predicting buy when actually the person or the test instance buys, and the classifier is not predicting, so it's predicting that they will not buy when they actually don't buy. Okay. And so in general, you'll see a matrix like this, and there are some names for each of these cells in this 2 cross 2 confusion matrix. We're gonna use true positives to represent when the reality was that they would buy and you predicted that they will buy. And similarly, false negatives when the reality is that they will not buy and you predicted that they'll not buy. Okay. And what we're concerned about is these things which are off the diagonal. Okay. And they are the ones which will lead to errors in classification. So instead of a single accuracy number, now we went to four numbers essentially in this matrix. Now, so with that confusion matrix, representation, now we can start talking about the business goal. Okay, and it's tied to in the following sense. Okay, we as a classifier, it will make some mistakes, but the mistakes that it makes is not all equal. In the sense, errors which are false positives and true negatives, these off diagonal cells, they may not be equally important. So let's consider a couple of examples. The first example is, let's say, in a health setting. So let's say the classifier is predicting whether this person has a cancer, which is a positive class, and versus no cancer. Okay, and so let's say it's a test, like a lab test. And so, which error is less costly, do you think? And so there are two types of errors, right? When you predict that there is no cancer, but there is cancer. Okay, and or you can do the opposite, which is when you predict cancer when there is no cancer. Okay, so majority of us would agree that maybe the first outcome is not good. It's too costly because we are saying that there's no cancer and this person, will not get, the requisite treatment and may actually, die. So let's think of a more milder example in a completely different setting. This is in targeted marketing. And so you have a bunch of customers you want to target. And so for each customer, you can say, oh, if I target this customer with an ad or a marketing, a coupon or something, will this person actually buy or not? So there are two types of errors that I'll make. I'll spend some effort, and there are two types of errors. First is I'll predict a customer is not going to respond when they will actually respond. Okay, so in this sense, I'm losing that customer. In the sense, if I had targeted to this person, they would have actually bought my goods, and so I would have made some money. But I did not. I predicted that they'll not respond, so I'm leaving money on the table. Second one is predict that they will respond when they actually don't. Okay, so in this case, I have spent. I think that they will respond, and I actually sent them a targeted ad or a discount, but they actually did not end up buying. Okay, so here it's a wasted effort. So these are so what the illustration of the slide is to say that there is a difference between the two types of errors that we are incurring. So next, let's look at how to now bring in costs and benefits along with the confusion matrix to get a better assessment of how my classifier is doing. Okay, in terms of my business goal, which is to make profit. So assume that we are interested in maximizing expected profit, and let's fix our example to be target marketing. So we want to evaluate our classifiers. So let's say there are two classifiers, and I want to know which classifier is good for me and works well for me in terms of making, maximizing expected profit. And so the way we're going to work with is we're going to look at all our test set instances. So maybe my test set consists of 100 instances, okay, for which was not used for training these two classifiers. Then I can say whether, using this test set, I can say whether the decision tree classifier is better or worse than an SVM classifier. Okay. And so the way we're going to compute an expected profit. So first, before getting to a plot, I want to compute an expected profit for a given confusion matrix. And so the way I'm going to do it is the confusion matrix has counts, right? Every test instance, I'm going to put it in one of the cells in the confusion matrix, depending on how well the classifier predicted. I'm going to normalize the matrix in the sense that I'm going to divide all the numbers in the cell divided by the number of test instances I have, so that each cell entry now corresponds to a number between 0 and 1, which is essentially probabilities. Okay, and next what I'm going to do is also create another cell which will have also create another matrix which will have 4 numbers, and those 4 numbers correspond to the costs and benefits of each outcome. Okay, so these 4 cells are essentially 4 outcomes, and so if I can have a sense of, depending on each outcome, how much my cost or benefit is, then I can compute some sort of an expected profit score. Okay, and so here's an illustrative diagram. Um, So let's say you had a data set and you created an algorithm, and here we computed a confusion matrix, which is a collection of true positives, false negatives, and true negatives. Then we normalize, which is just divide each of these entries in this matrix by the total number of test instances we have. Let's say it's 100 for simplicity. Now we have this matrix. Okay, this is the matrix of probabilities. Now, what we also want is a cost benefit information, and it's also going to be a 2 cross 2 matrix, and each entry, each of the 4 cells will have a number. It just says, oh, if if the ground truth was actually they will buy, and I predicted that they will buy, how much is it going to benefit me? Okay, and so there's going to be some score, let's say plus $100 or something. So similarly, there will be three other numbers. Okay, so what we're going to do is do an element-wise multiplication. So we'll multiply the first cell with the first cell, the second cell in the first row with the second cell in the first row, and so on. We'll multiply them together, and then we'll get four numbers. We'll add them together, and that's my expected value. Okay, so that's my average profit. Okay, for this classifier. Now, so here's the most interesting part in this lecture is that, so that's for a specific classifier. There was a confusion matrix, and we computed a expected profit. Okay. Now we want to extend from that single profit number that we computed to a visualization, which is called a profit curve. Okay. And the key idea here is that many classifiers actually don't just output a binary yes or no, whether they'll buy or not, but also actually output a score. Maybe 0.9, which just means that maybe they're highly likely to buy. Maybe 0.1 represents that maybe they're not likely to buy. So let's say we still have our 100 test instances. So we're gonna look at them as a collection where for each test instance we have a prediction, which is a number, let's say between 0 and 1. Okay, so this is what I'm calling as scores. So what we're going to do is sort these test instances according to my classifier's predicted scores. Okay, so the guys for which I think they will buy, I'll have a high score, 0.9, 0.87, whatever it is, and so these instances will be at the top. Okay, once we have this ranked list of test instances, then what we're going to do is um, we will intuitively try to act on the instances at the top of the list. So the instances at the top are the ones which will actually buy. So that's our hypothesis. I mean, that's what the classifier is saying. So and why does this ranking and sorting make sense is because, when we have a fixed budget for targeted marketing, let's say we only have $300 to spend, then we can spend most of our effort in for those test instances where we think that they're most likely to buy. Okay, so now we have this ranked list of test instances. Now the way we can work with is that if we can create we can use these scores and a threshold as a specific number. A threshold is a number between 0 and 1. Using the scores and the threshold, we can create many confusion matrices. Here is an illustration of what I mean. So these are my test instances. Okay, true classes, we will have this information, but here is the most important column, which is the scores. This is the scores that my classifier is giving. I can change the scores depending on different classifiers, but let's say a single classifier gave me the scores. I sorted them, so you can see 0.99 is greater than 0.98 and so on. And then I can have a threshold. Okay, so because now I have scores, it's not just binary. Scores with a threshold gives me a binary classifier and therefore a confusion matrix. So think of it this way. So if my threshold is above the highest score, then there is absolutely no test instance which was positive and was classified positive. In fact, there are no test instances which will be classified positive. Okay, so if my threshold is between 0.9 and 0.98, you can see that the first test instance is actually a positive class, and I'm trying to classify so anything above the threshold to be positive. So therefore, I increment this cell by 1. And similarly, if I go one more level below, there is an increment of 2 over here. Okay. And so this is now generating me or giving me a sequence of confusion matrices, and for each confusion matrix I can use that cost and benefit numbers to compute an expected profit value, and that is precisely a profit curve. Okay, so you keep moving the threshold down the ranking and obtain a sequence of confusion matrices, and for each confusion matrix you can compute the profit. Okay. We can also compute we can also compute another quantity, which is, at each threshold, we can say how many positive predictions there are. Okay, so maybe if for example, the threshold is really high, there is no positive predictions. If the threshold is between 0.98 and 0.96, then there are 2 positive predictions and so on. There are 2 positive predictions. Yeah. So here is an example of a profit curve. Okay, so here the percentage of test instances. So all the test instances is 100 over here, and at various levels of percentage of test instances, you can see how much is the profit that the classifier is giving me. So so at each, let's say a threshold which gets up to 40% of the test instances, which means that if we sort it, there is 40 let's say number of test instances is 100, then the 40 above and 60 below. So for 40 of them, I'm going to predict as positive, and remaining 60 as not going to buy. So, and then I can just compute the confusion matrix, and there's going to be some maximum profit. Okay, some profit, sorry, that I'll get. And once you look at this curve, you can look at what is the maximum, what is the minimum. If I'm only interested in the top 10% of my predictions, how much is going to be top 8% of my predictions, how much is going to be profit, and so on. Okay, and you can also compare classifiers, and this is a very good representation for bringing in business objectives with the classifiers, raw performance, which is the given by the confusion matrix. Okay, and here this slide explains the same thing as what I just mentioned. So let me now talk about the next two curves, which are, first one is called cumulative response curve, and the next one is called a lift curve. So these are actually very similar ideas. So here the key idea is to plot the true positive rate. Okay, so now here we are dropping the cost benefit numbers because first of all, cost benefit numbers itself you may not know exactly. So the key idea is to plot just the true positive rate. Remember what true positives are. True positives are the numbers, are the counts in this cell of the confusion matrix. So the true positive rate is just the percentage of positives which are correctly classified. Just let's focus on just the first column. And in the first column, there are some numbers, some instances that we have correctly classified, some numbers which we did not correctly classify. Okay, so the true positive rate is just the first cell divided by the sum of the first two cells. Okay, in this column. Okay, and we can compute this number at every level. So as we keep changing the threshold again from top to bottom, we are classifying more and more instances as positive. And so the question is, are we are we getting a larger portion of actual positives when we are at the top of the list? So for example, at 40%, which means that in a test instance, number of test instances is 100, 40 of them at the top, we have classified them as positive. What percentage of them are actually positive? Okay, so you can see that about at top 40 that are classified as positive, about 75% of them are positive. Okay, so these curves are and ABCD just represents 4 different classifiers. Okay, so this is another instance of an intuitive representation for business stakeholders. Okay. And lastly, the idea is the idea of lift curves. It is just an extension of the cumulative response curve. And here the idea is the degree to which the classifier pushes up the positive instances compared to negative instances. So in the previous curve, it's just how many positive instances did the classifier push up. But here, lift is just a relative number. So it's how many instances did it push up at a given threshold compared to instances below. Okay. So this is actually equal to the cumulative response curve at a given x value divided by x. So for example, at 40, there's a percentage which is like about 70%, and the lift value at this x, which is 40%, would be 70% divided by 40%. So that's a slightly different representation, but also captures the idea of how well you're doing. So if you consider about let's say 1,000 customers, and let's say half of them respond to marketing and half of them don't. Okay. And let's say we want to target the top 50% based on how my classifier is predicting. So if the classifier is actually a random classifier, it's not really doing anything, then we expect 50% of this the subset, in the top 50% to be truly positive. Okay, they will respond to marketing. Okay, and so the lift of a random classifier is going to be 50% who will respond divided by the 50%, the percentage that the top 50% that we're taking. So that's division is equal to 1. But if it's a perfect classifier, so every person who is actually going to respond to my marketing ad, they will, we know exactly that's the perfect classifier. That's the prediction of the perfect classifier. Then we expect 100% of this subset to be truly positive because of the way our data set is. And so here the lift is going to be 2. And so you might have seen at some places people talk about, oh, our new model is going to give a 2x lift. So this is a type of statement you can make when you compute a lift curve. Okay, and the lift curve looks very similar to the cumulative response curve. The x-axis is again percentage of test instances. So in the top 40%, how much is my lift? So here you can see that the lift is a little bit less than 2. Okay. So it would have been 2 if, so at 50, for example, the lift would have been 2 if the classifier was a perfect classifier, which in this case is none of these are perfect classifiers. Okay. So with that, let me summarize what I was trying to convey in this module. you can properly evaluating your classification models or prediction models is important and requires going beyond a single number, which is accuracy or loss value, okay, on the test set. And the expected value framework is uses both the confusion matrix in the classification context, as well as cost benefits information to give us a sense of how much profit or how much bang per buck there is for a given classifier using a given classifier. We can so this evaluation can be business goal oriented, or evaluation of classifiers can be business goal oriented using the three curves that I mentioned: profit curves, cumulative response curves, and lift curves. And and these are visual in nature, so they are very intuitive, can be made intuitive sense to business stakeholders. With that, thank you so much for listening.